Okay, I'm Carlos. I'm a PhD student at the Instituto de Astrofísica de Canarias, and I work on massive stars, specifically in O-type stars. So the first question, easy, it's what is a massive star? It's a star over 8 solar masses. And we always say that, okay, they are the key elements for understanding the chemical evolution of the galaxies, but they are interesting objects by themselves, and we want to understand their evolution. They cover a huge range of spectroscopic in the spectroscopical HR diagram, but I'm centering in O-type stars in the main sequence. So I just wanted to remember you two main points. Is the main energy production. In this case, it's by CNO cycle, and that's talks about the structure that is formed with a convective core and a radiative envelope during the main sequence. But already in the 90s, it was discovered the so-called helium discrepancy, which is an overabundances in helium and other CNO products in the surface of the star when in a non-expected evolutionary state, when it's too young. So different theories were proposed for solving that. Two main theories was, okay, a more efficient a higher mixing efficiency, which would be traduced in contamination in the surface or binary evolution. In this case, we can have both. As usual, we have been talking about it for the last few days, a common envelope or Roche law of overflow. I'm centering in this last case, and it's interesting because the theoretical predictions said that due to this infalling material, there should be an acceleration producing a tail when we do the velocity distribution, the projected rotational velocity distribution. So this is theoretical predictions. Now, what is my work? Well, my work is working with the IACO sample that contains now like 400 Omin sequence stars with parameters, especially with projected rotational velocity, gravity, helium abundances, and temperature, effective temperature. And from this complete sample, taking a subsample of lower rotational velocities than Nicolai's sample. So it's complementary. It's lower than 150 because I will try to get the N abundances with nitrogen abundances with the equivalent width method using Fang-Shui models. So we need strong lines. In higher velocities, the lines are much shallower and it's much more difficult to get abundances reliable. After doing that, I have got 164 stars with reliable nitrogen abundances with no special distribution in the HR diagram. The only point is, okay, they are not so much close to the us, but more or less distributed uniformly in the spectroscopic HR diagram. And if we compare with helium abundances that we already had, and Nicolai also showed something yesterday, we got this plot. What's interesting about this plot, it's the theoretical prediction in single evolutionary models, because all the models has a very clear trend, which is the product of the CNO cycle. So it has this form. In some models, more mixing efficient, it's higher. In other models that are not mixing efficient, this is equivalent to the broad models. It's slower and it will continue after the main sequence. This is only covering the main sequence at this point. So we see something very interesting that the distribution is very narrow. It's not so dependent on the projected rotation. Bueno, in that case, they are theoretical prediction on the rotational velocity. And also, we can see that in all cases, nitrogen enrichment is much faster than helium enrichment, which means that we cannot see helium, we don't predict by single evolutionary models to see helium in the surface without previous nitrogen enrichment. For the sake of simplicity, I will summarize all these models with a shadow area in this plot, and I will also add two reference points, which are the abundances from early B stars in the Orion Nebula and H2 regions. And we see that here, most of the stars follow the trend, the theoretical predictions, but there is an interesting group, which is this one, which is helium enriched, but not nitrogen enriched. This is, of course, not predicted by single evolutionary models. Okay, but maybe our models are incorrect. Maybe they are an evolutionary state. If so, we would expect them to find them in a particular region in the spectroscopic HRD diagram. But it's not the case. They are, again, uniformly distributed. Okay, in that case, we don't have stars close to the thumbs. That's the only point. Okay, second theory. Maybe it's because we have wrong initial conditions. These initial abundances, it's overestimated. If we compare with H2 regions and we expect the O stars have the same initial abundances as the H2 regions in which they are formed, or if we compare with early B stars, which should be the comparison. For studying that, we can completely ad hoc, just moving our models to match the H2 regions. If we do so, we see that the problem is not solved, it's reduced. We still have 7% of the sample that are helium enriched, but nitrogen normal, or in this case, even poor. And again, if we go to the spectroscopic HRD diagram, we see something more interesting, that is those stars are expected to be more or less evolved. So we would expect them to be nitrogen enriched if it's a mixing point. So maybe they are possible post-mass transfer products. The only point that we can think that can enrich helium without enriching so much nitrogen is if we have an already enriched donor that is nitrogen poor in the surface with a mass main sequence gainer. This could make it, but in this case, we want to add some more information, especially about possible binarity or previous binarity. SV2s were excluded because it's not easy to get the parameters. SV1s have different origins. We don't see the companion, but it can be both a low mass or also a black hole or a super star that had gone through mass transfer events previously to get stripped or the supernova event. And also runaways are interesting. Why? Because they can be both produced by dynamical interactions, not interesting for us, or again, supernova, that disrupted binary at the supernova kick. That again could be interesting because they could have previously gone through mass transfer events. So if the helium enriched is produced by mass transfer, we would expect higher number of SV1s and runaways. If we do the statistics, we see that in the case of SV1s, it's not fulfilled. The proportion of SV1s in both groups, helium enriched and not, it's exactly the same. Okay, we have to think again that it's most probable for a massive star to have a low mass companion than to have a superstar or black hole. So that can reduce the problem. And in the case of runaways, it's 50% higher, but with the errors, we can say nothing. Okay, can we say something only with helium because the sample is much greater considering only helium? Well, as we said, we expected a higher projected rotational velocity after mass transfer. If we go to the histograms for the helium distribution, we see both a peak displacement that can be attributed to the uncertainties in the error in the velocity measurement, but also that the tail, it's much more important in the case of helium-enriched stars. If we do the Kolmogorov-Smirnov test, we see that it's almost impossible those two subsamples to come from the same sample. This one, by the sake of simplicity, this is the helium-enriched sample. So the sample that we expect to be post-mass transfer, but you can say this is expected from single evolutionary models because you have an important mixing, a much more important mixing. Okay, we have to remember here the discrepancy we had between nitrogen and helium that is not solved by adding more stars. So it's not expected by single evolutionary models, and we can also say that not only the helium or the nitrogen are enough for going through the mass transfer or the single evolutionary models. So we have to get abundances of both parameters and more elements if possible, as Nikolai was showing yesterday. And that's it for my side. I will let you hear my conclusions or a summary of the presentation, and thank you for the attention.
Great, thank you. Questions? I can, Tomer's got one.
Thanks for these results. So yeah, you have quite large error bars, which I know it's difficult to measure the helium abundance, but did you consider the fact that maybe these are outliers due to, you know, systematics problems with the normalization, maybe even binary contamination?
Yes, they can be. In this case, they should also affect the temperature. That's another point. But we have reanalyzed this. Well, first, I want to say that this sample has increased respect to Gonzalo's result, but also has been reanalyzed with a much smaller grid. So the errors are more difficult. They can have contamination of binaries, but still the sample is great enough to overlap these errors. Of course, I mean, they shouldn't have large errors because we have multi-epoch spectroscopy, and those SV1s that are detected as SV1s are already studied as those, and the SV2s are removed. So contamination from SV2s, which is much more important, is not considered. There shouldn't be contamination or an important effect of contamination in those cases. And SV1s shouldn't be so important because the companion is not detected in the multi-epoch analysis that we have been made.
Great. More questions, comments, thoughts?
I have a question, if I may.
Yeah, go for it, Helium.
Yes, thanks. Thanks for your talk. It's very interesting. Perhaps I missed it, but I wonder if you consider this initial carbon and initial oxygen abundances that might cap the nitrogen enhancement that the stars can reach. Did you explore this?
Okay, this is always a theoretical problem. I don't do the theoretical models, so I'm not so expert on that. But we have matched in all cases the initial abundances from external models to be consistent. But okay, you can the same problem that we have with H2 regions and the Orion Nebula are also considered or are also reproduced in the case of carbon and oxygen. However, both the measurements of carbon and oxygen are much more difficult, and it also affects to the initial abundances that we have to consider. It's not so easy to do from the observational point of view. But answering fast, not so much. It's an interesting point for doing or redoing models, recomputing some models.